AI systems. Well, I've got some good news and some bad news. The good news is it actually looks fairly familiar in a lot of respects. Bad news, or bad news for some people, is that we're going to have to alter the way we're thinking about it. We're going to have to alter our perspective, our point of view as we're approaching some of the things we already know that we do well. Some of the areas that we're going to have to focus on are going to be slightly different. Now, for me, that's a good thing because I'm curious and I'm a learnaholic. So I love learning new things. Some people aren't quite so keen on that. We're not going to have to think in a slightly different way. So we'll start off with some of the challenges around how do we test AI. Some of the things we need to think about. First off, we don't have an oracle. So we've got nothing to compare it against. So the old-fashioned way of having expected results, what some people call checking or verification, old-fashioned testing. We haven't got those expected results. We can't go tick. It's non-deterministic. So you run it 2 or 3 times, you're not necessarily going to get the same answer every time. And the answers are probabilistic. You won't get, it's definitely this, or it's definitely not this. You'll get probably within this range, maybe this. So the code does not actually represent the data. Often, high volume, they can be very complex. These systems, because they're self-modifying, are also self-optimizing. Their behavior is going to change over time. Which means that you have a higher system. Especially since a lot of the tasks that we're trying to use AI for, we're doing that because they're complex. We don't want to do them as humans. We want something to do it for us. We're also trying to mimic human abilities. Human abilities, by their very nature, are very difficult to actually write requirement specs and designs for. It's not that straightforward at all to say exactly how we behave. Look how long it's taken for us to get an Android type robot to actually move like a human. They still don't quite do it. And the problems of bias are very well known. Anybody that's listening to any of the IT news streams or on LinkedIn will know about the bias issues. And of course, the hallucinations. We all like to have a laugh at the hallucinations. I actually prefer the term confabulations because that's the psychological term. It's what humans do. If you ask humans questions repeatedly on the assumption that they know the answer and they know that you're assuming they know the answer, sooner or later their brains are going to make up an answer, which is exactly what AI is. And finally, how do we measure test coverage? It's a completely different paradigm. So what do these test levels, these test stages look like? We've got some familiar ones. We've got the usual unit or component test, integration testing, end-to-end testing, and of course, everybody's favorite UAT. And then we've got some that aren't quite so familiar, model testing. I see quite a lot of chat about this in the forums about model testing and on LinkedIn. Also, have data testing, considering that the algorithm isn't necessarily what actually drives the behavior, it's the data that's fed it. That's important. And then finally, monitoring test. The monitoring in live, a lot of people don't consider that to be a test phase, but should. It's all part of the quality engineering, it's all part of the DevOps philosophy. So therefore, we have to consider that very carefully. And I'll explain more on that later. So, taking the first one, component test. Traditionally, that's been black box testing or possibly white box testing. So, How do we test against requirements when one of the descriptions of AI is automation without requirements? You can't. And if the code is not actually the algorithm, the code is not the behavior, we can't do white box testing. We can't go down to the code level and test the code. That doesn't make sense either. But all these AI components that fit together have to have data feeds. They have to have input data and output data of some form or other. Even if that's only a UI that's feeding it, it still has to have a data feed. So we can apply all those old-fashioned skills that we know so well as testers. We can try messing with the input data. We've got an input field. Can it handle false zeros, out of range values, blanks and nulls? Messing with the format, duplications of data. Can the actual input pipeline handle those error conditions? Likewise, within the UI, mess with the UI in the same way that you would with any other UI. And that data, because the data dictates the behavior, is really important. This is one of the crucial areas that we need to test in the data testing. So we have to test for bias and fairness. But bear in mind that there are proxies for bias. For instance, address. Address can identify your race, your status, your income. In my area, your age. The average age in my postcode is 70. I bring it down a little bit. And then we've got data diversity and representativeness. Bear in mind, it's got to be representative of the environment where you're going to be using it. So diversity, yeah, you want the biggest diversity you can get, but it's got to be realistic for the environment. Take facial recognition that's been performed in, say, Manchester. It's been developed there. It's used a diverse amount of faces from Manchester. You then take that to Japan, it's going to really struggle. You want a different diversity for that representative set. The way you categorize your data is also crucial. If the granularity of your categorization is too big or too small, that leads to errors. It leads to false categorizations. Generally speaking, with models, you train them using a large data set. And rule of thumb is that 80% of that is for training, 20% is for testing. So you split the data up. That can cause problems. If when you split the data up, you're not splitting it up in a manner that's suitable. For instance, if your test data set is a small subset of the larger data set, isn't representative, you have a problem. You don't want to do just happy path, you want outliers. You want to make sure the outliers are in that test data. And how we do it, it's through statistical analysis. Now, statistical analysis is a degree subject in its own right. In fact, you can do PhDs in it. So, data scientists are our best friends. Buddy up with them. Find your local one and get really friendly. We don't need to dig deep into that, but we do need to know someone that does understand the detail, because we can help them do it better. Then we have integration test. And this is a really familiar one that we're probably all very aware of, but there's a complication. Because AI is probabilistic, it means that when you integrate more than one AI unit together, the error factors multiply. This is particularly interesting when you talk about things like facial recognition, because the first thing you have to do is go huh, that's a face. And then you go, whose face is it? Now, if it can't even identify the face of a chihuahua compared to a blueberry muffin, you've got an issue there. So that error factor, when you then try and identify which chihuahua it is, that is going to get multiplied out. Like I say, the probabilistic is each of these has a probability of that being a chihuahua. It's not an absolute. Don't forget the error factor is multiplied. Take that into account. See the chihuahuas twice. How cool is that? And then model testing. This is an entirely new level, but one that gets talked about an awful lot. So the primary focus for this is models performance, behavior, and predictive capabilities in isolation from those surrounding it. This is statistical in nature. It involves very large quantities of data. If you use small data sets, then you're not going to get a representative model of what's happening when you put it live. It tends to be very complex to interpret what the outcomes are because it is statistical in nature. Data scientists are our best friends. Put you up to them. But there is still benefits from us being involved with the data scientists because they're just as liable to bias and problems. Quick anecdote, I worked with a company a while ago. They had an AI solution for optimizing fraud detection. They were just about to roll it out into a bank. I was talking to a project manager and he went, could you have a look at how we've tested this, please? Basically, they hadn't, because they hadn't done all the testing around the data to the extent that they needed to. And it was obvious. It wasn't that I was particularly an AI guru. I was just a tester looking at it going, gaps, missed stuff. Simple stuff. The sort of thing that any of us here could do. Here's a quick sample of some data that we use. At 2i, we've got a synthetic test data generation tool. And this was from an early run. And as you can see, the black lines are the real data that we're comparing with blue lines, which are synthetic data. And as you can see, there's errors in there. Take that away, we can refine the model, we can make it better. Same again here, similar sort of thing in this outline at the top end. Here you can see there's quite big gaps. So that's the sort of statistical analysis you can do on the data, comparing what you want to what you get. Same again there. End to end, again, very familiar. But again, beware of that complexity. Beware of that multiplying of the error factors. And if the system that you're trying to create is based on an expert, or a guru, or an oracle, then employ that oracle, that expert, to actually help you decide what's right and whether it's actually working, what's good. UAT, that's the level that we all know and love, and it's pretty much the same. But be aware of automation bias. Believe it or not, humans have a propensity towards leaving automated decision-making systems over and above humans. It's the classic computer says, no. I mean, why we do this, I'm not quite sure, but it's a documented research propensity. So always be aware of that. Always question what the output is. And as I said, monitoring live generally doesn't be considered to be a test level, but it's absolutely if the performance of an AI system detecting cancers degrades, then the impact of that is significant. Monitoring live. And what we get is a thing called drift. There's two main forms of drift. There's context and there's data. The context drift is when the context within which the model is working has shifted, it's changed. So, for instance, spam detection. And the spammers changed the way they're behaving. So the content is no longer identifiable as being spam. There's other factors that shifted. It no longer works, it no longer performs. And then data drift. There was a bank that was using an AI system for loan application recommendations. And then COVID hit, furloughs. Suddenly, the data that was coming in for these loan changed. The whole format, the profiling had changed completely. The model had to be retrained. And that was down to data drift. And then there's all the other usual stuff. So accessibility, usability, security. I'll talk about adversarial testing in a moment. And performance, but bear in mind, performance is not how fast we do stuff. That can be one of the factors, how fast and how much, but it's also accuracy, precision, and recall. The slides will be available, and I'm talking exceedingly fast, and I realise that. But you can have a look at the slides, and the slides have got notes on them as well, so it explains an awful lot of this. And there's tools for measuring accuracy, precision, recall, F1 score, and all this sort of stuff, and you can look it up online. So, quick rundown of test techniques that are available to you. The first one, explainability isn't actually a test technique. It's a legal requirement. Any decision system has to be explainable so that you can query it. For instance, if you apply for a loan, it gets rejected, you can say, why was it rejected? And they have to be able to tell you why. So you can get tools you can embed to improve the explainability. And according to the EU AI Act, which is a bit of a mouthful, all AI systems have to be explainable. A/B testing, we already know about A/B testing. Basically, two systems, see which one works best, which gets the best responses. Parallel testing is comparing the new system, AI-based, with the legacy system. So the legacy system is still running in live and still doing all the work. The AI system runs alongside it, you compare it, and then at some point you swap over when you're happy. Statistical analysis, I've already mentioned that. Exploratory testing, I think from a previous hands up, most people know what exploratory testing is and have done it. Well, AI is an absolute fertile ground for exploratory testing, especially LLMs, ChatGPT. They're not the only fruit, but yeah, exploratory testing is the way forward with that. Use experts if you got them. That gives you an oracle. Otherwise, or orthogonal testing, it's a bit old school, but it's a mathematical technique where you can reduce the number of permutations drastically to from say 2 million down to 200, 250, which is a big scale. There are tools for that. Metamorphic testing, where you actually change the inputs and see what shape the outputs change in. So you're not looking for the actual data change. You're not going, well, I moved that by 1, so therefore that must be moved by 1 or 2 or whatever. It's a case of that went up, so I expect this to go up in some way. That went down, I expect this to go down in some way. That avoids the oracle problem, sort of sidesteps it, because you're looking at the form of the change, not the detail. Adversarial testing. Now this, because the data dictates the behavior, if you mess with the data, you mess with the behavior. It's like chatbots now. Microsoft chatbot that started off as I love humans, aren't they cool? And then within 24 hours, it turned to extreme Nazi. Basically, the data was messed with. And the current attack is the Minja attack, which is basically poisoning the data well that's used. Model back testing, you basically use an old data set where you know exactly what should have happened, feed it into the new AI model, see if it does exactly the same. Algorithm ensemble, basically use a bunch of different algorithms, different models, run them all together, same data sets, see what happens, see what gives you the best answers. Coverage data. This is making sure that every node within the network lights up at some point. It's a bit like code coverage. You can do it if you want to, but I don't think it's going to actually tell you anything. So treat that one with a little bit of skepticism. Cross-validation. This is where you take the data set that you're going to use. So I was talking about the 80-20. So you take your data set, you split it into so many subsections. You use the first subsection for testing, the rest for training, and you record the output. You do it again, only this time you use the second subset and the rest of them for training. You record the output, compare it to the first. Then you do it again with the third, the fourth, the fifth. However many subsets you're going to break it down into, repeat it. That way you make sure that you're using a good data set for your testing. And then affordance modeling, this is one that's used in UX UI. It's a very old-fashioned idea that things that are designed to with their function in mind, for instance, that mug has a handle on it. So you pick it up with the handle. The idea being that if you understand how it's supposed to be used just by looking at it, then it makes the usage of it more likely. So I've really quickly gone through testing tools. So you've got your toolkit. Now you can fit that into your quality engineering. Quick definition of quality engineering: it is essentially building in quality throughout the whole of the process. So these tools can be used throughout the process. You can now use those tools to form a quality assurance framework. The quality assurance framework is making sure you've got the measures, the mechanisms, and the governance in place to be able to build the quality in engineering. And 2i, we've got our own framework called Assure AI. If you go away and you get the experience and you get your AI gurus together, you can form your own framework. But essentially, you're going to be using the same tool set that we did, or I've just given you there to do it. For instance, these are the 4 factors you're looking at, and within the accuracy factor, data integrity, so that's your data testing. Model validation, that's your model testing. Continuous monitoring in live. And the compliance and standards stuff, well, it might stick to the compliance and standards, but is it good? Does it work? And likewise, data diversity, adversarial testing, user-centric design, transparent algorithms, all these things fit into it. And that, you can basically go, I've got the right measures and metrics and governance in place, so I should be able to build quality in AI system. Hopefully that makes sense. I'm galloping through this at a rapid rate of knots. Let me get down to that slide. Like I say, you can have the slides. These have got links on them. Useful resources. Beware Hugging Face. It's really good. It's really useful for them. Loads of stuff on there. I've used lots of the models off it. But bear in mind that line actors have been known to post on it. So, but loads of stuff to learn from there. Monkey-Learn's good. Scikit's good. SciPy is the standard toolkit for Python AI generation. So much in there. It's a rabbit hole if you're not careful, but it's brilliant. TensorFlow. Likewise, PyTorch, that's another good toolkit. So, if you want to know more, if you want to talk to me, find out more about it. If you want the tool, the slides sending to you, let me know. And incidentally, I also host a podcast called Quality Blether. So, talk to lots of different people on different sort of topics of quality, including AI, amongst other things. Come talk to me. I do have merch, so come say hello.